Our next speaker is Felix Brandt. Felix, the floor is yours. Please start.
All right. So thanks very much for having me. So I'm delighted to be part of this conference. In my talk, I will introduce a randomized dynamic voting process, which is based on drawing balls from an urn and modifying the contents of this urn based on the voters' preferences. So this is joint work with Florian Brandl, who I believe is also still in the audience. So there isn't much going on in the forum yet or on the chat yet, but I think if you have quick clarification questions, you can ask them in the forum and then Florian will be happy to answer them. And otherwise, you can just shout out loudly and interrupt me and I will try to do my best to answer any questions. Okay, so the title of this conference, New Directions in Social Choice, I think is quite fitting for this paper, because we try to challenge some of the basic assumptions in social choice theory. So these assumptions are not made everywhere in the literature, but they are quite standard assumptions in the default setting that we are all familiar with. So by this setting, I mean the setting where we have a preference profile. So we have voters with preferences, and then these preferences are mapped to a single winner or a set of winners or a lottery over winners. So in this default setting, we have a fixed set of voters. We also have a fixed, well-defined set of alternatives. And we assume that voters are able to rank order all the alternatives, which can be quite a demanding assumption if you have a lot of alternatives. We also assume that preferences are fixed because the standard setting only talks about a single election. And there's this assumption of a central authority which collects all the preference relations, is able to compute the election outcome, which we know can be quite a demanding task. So there are some voting rules for this, is quite difficult. And also the central authority has to convince the voters of the correctness of the outcome. And this can be a particularly challenging task if you're talking about a randomized rule, because in that case, voters not only need to be convinced of the correctness of the outcome, but also of the fact that the lottery was executed faithfully. So by contrast to this setting, to the standard setting, the goal of our paper is the following. So we intend to devise an ongoing adaptive voting process that satisfies desirable axiomatic properties. So first, voters should be able to arrive and leave the process and change their preferences over time. We never ask them for the complete preferences, so rather only small parts of the voters' preferences are elicited on demand. So in particular, we query voters for isolated pairwise comparisons whenever necessary. And rather than having a central authority, we want to use one simple physical device, namely an urn that is filled with balls. And these balls are labeled with the alternatives. And on this urn, we only need to allow for two primitive operations. The first one is to randomly sample a ball from the urn, and the second one is to replace a sampled ball of one type with a ball of another type. So this simple urn device is the only thing that we need from a computational point of view. So let me just start really by describing this process that I have in mind using an animation. So here in the example, we have a fixed set of 4 voters, but as I said, so the number of voters can vary over time. And then we have an urn that we are going to fill with balls. So each ball is labeled with an alternative. In the example here, we have 4 different alternatives, A, B, C, D. The initial configuration of balls in the urn does not matter. Okay, so it's irrelevant for the process that I'm describing. Now we put all of these balls in the urn, and then we select one of the voters uniformly at random. Okay, so let's just assume that in the first round of this process, it's this woman here. Then this voter gets to draw 2 balls from the urn. For example, it could be the balls marked with alternative A and alternative B. And then this voter is asked which of the alternatives she prefers. So in the example, it could be the case that this voter prefers A to B, and then A would be selected as the winner of the current round. Okay, so A is the winner. And on top of that, we are going to relabel the losing ball here. And we are going to relabel it with the color of the winning ball. So this yellow ball here will be recolored as a green ball because the green ball won against the yellow ball. And then both of these balls are put back into the urn. And this describes one round of this process. And we keep on doing this. So we select one voter uniformly at random. This voter draws 2 balls which you cannot see in the animation now, but two balls are drawn in every round. The voter does a pairwise comparison, and then we just get winners of each round, and we slightly modify the distribution in the urn during this process. So there's one thing that I didn't explain yet, which is part of the process, so one missing piece. And this is because maybe you've already noticed that we just define the process as I just did. Then there's the possibility that we are running out of balls of a certain type. So it's quite possible that after a certain number of rounds, for instance, there are no more yellow balls left in the urn. So some types of alternatives can go extinct. And this will actually happen with probability 1 if we keep on running this process forever. And in order to avoid this, once in a while, we are just drawing one of the balls uniformly at random. And then we just relabel it with another random color. Okay, so here we have drawn ball with color C, and then we are relabeling it as yellow ball labeled B, and then we just continue the process. And now that really completely describes the process that we present in the paper. Okay, and now you can ask many questions about this process, but one of the key questions that we are interested in is what can we say about this sequence of winners here? Or perhaps more precisely, so what can we say about the distribution of winners? So does it converge? And if it does converge, against what does it converge? And this is what we are studying in our paper. But before we get to answer these questions, let me just formally, or a bit more formally, summarize the urn process that I described. So we have an urn filled with n balls. So capital N, you should recall, is the number of balls. And each of these balls carries the label of an alternative. As I said, the initial distribution is irrelevant. So for instance, we could start this process by having each voter put one ball of her choice into the urn. Then in each round, a randomly selected voter will draw two balls. If these balls would be X and Y, and this voter prefers X to Y, X is the winner of the round. And the losing ball Y will be relabeled with X. And then both of these balls, which are now labeled X, are put back into the urn. So by the way, if we have indifferences, so we don't need strict preferences here. If you have indifferences, the process just works fine as well. So then the voter just arbitrarily picks one of these two alternatives. And finally, so
Felix,
yes.
Sorry for interrupting. There is one related question on the chat from Edith. She asks, what happens if we draw two identical balls?
Okay, so that's a good point. So if you draw two identical balls, well, then there's no choice to be made by the voter, and the voter just selects the ball, any of the two balls, and that will be the winner of the round. And nothing is replaced. Okay. Okay. So drawing two identical balls is just fine, just for the sake of the example here. I assume that they are different because that's the more interesting case. And yeah, so with some small probability R, we are randomly changing the labels of balls. So we basically have two parameters here. So N is the number of balls, and R is what we call the mutation rate. These are just these random changes for balls. Okay, now let's talk about our main results. So first, if you think about this process, I think it's intuitively clear that the actual urn distribution does not converge. Right? So this is because we have these random mutations. And if we didn't have these random mutations, then the process would end up in a degenerate state with probability 1, and then we would also wouldn't have convergence. So the actual urn distribution doesn't converge, but as I said previously, we are interested in the empirical distribution of winners. And here, our result says that if the number of balls in the urn N is sufficiently large, then the empirical distribution of winners almost surely converges to a lottery that is close to a maximal lottery. So I haven't really specified yet what maximal lotteries are. I'm going to do this in detail in a couple of slides. So for now, you can just think of a maximal lottery as a specific lottery over alternatives that has desirable properties based on the preferences of the voters. So it's maximal lotteries is a randomized voting rule. And here in this theorem, we say that this process converges to a lottery that is close to a maximal lottery. And as you probably can imagine, so how close it is depends on the mutation rate R, because that introduces extra randomization in the process. And the smaller we make the mutation rate, the closer we get to a maximal lottery. However, we cannot set the mutation rate to 0 because, as I already explained, otherwise the process ends up in a degenerate state and it doesn't converge at all. So since this is a bit difficult statement to formalize, so I also need some formulas. So in contrast to Markus's presentation, I couldn't just only do animations and pictures. So there are some formulas in here. So here, that's the formal specification of the result. So let me just walk you through this. So we have some delta greater than 0, and that's the distance from a maximal lottery. Okay, so and then for this fixed delta, we say that there's a lower bound on the number of balls and some mutation rate R, such that for all numbers of balls that exceed n0, or at least n0, and for any initial distribution, the following statement here is true. And here you first need to know what x is. So xnr ks0 is a random variable that describes the earned distribution in round k. So it depends on the number of rounds, on the current round, and the initial distribution, and of course on these two parameters n and r. And we divide this distribution in the urn by n to get an actual probability distribution. So numbers should be between 0 and 1. And then we just take the time average over this. Okay, so small n is the number of rounds. Take the time average and we let the number of rounds go to infinity. And what this statement then here says is that the probability that this limit here is within a delta neighborhood of a maximal lottery. So B delta is a delta ball around the set of maximal lotteries, that this probability is actually 1. Okay, so the probability will become higher and higher the more rounds we have in the process. But if we keep on running this forever, this probability will be 1. Okay. Okay, I'm just having a look at the chat. Yeah, sorry, it's not something that I'm going to enter right now. Let me try to give you some more insights into our results. So this statement here is a statement about the time average of earned distributions, and it still leaves the possibility that the distribution in the urn is never close to a maximal lottery because it cycles around a maximal lottery with a fixed or maybe even increasing distance. So therefore, what we actually show in the paper is a stronger statement. I just wanted to show you this one first because it's easier to digest. So what we show in the paper is that the earned distribution is almost surely close to a maximal lottery for most of the time. Okay, in order to state this here, we need the so-called sojourn time here. So for this random variable x that I introduced on the previous slide, we are now defining the sojourn probability, the sojourn time. And the sojourn time is the fraction of n rounds, if we are running this process for a finite number of n rounds, in which the earned distribution is within a delta neighborhood of a maximal lottery. Okay, so the sojourn time is a number between 0 and 1 that says for which fraction of rounds we are actually close to a maximal lottery. And then the statement here says is that we can just fix some delta and some tau. Now the tau is the new addition here, and the tau is just the fraction of rounds for which we are not close to a maximal lottery. We can just fix it arbitrarily, and then for any of these two parameters, we will find a lower bound on the number of balls and some mutation rate, such that the limit of the sojourn time will be at least 1 minus t, with 1 minus tau with probability 1. Okay, so this means that we can make this process arbitrarily close to a maximal lottery for arbitrarily long fractions of time by setting these two parameters, delta and tau. Okay, so there's one more mathematical statement before I will show you a lot of examples and details. So the limit statement that I've shown you doesn't say anything about the speed of convergence. So it could be that this process just converges extremely slowly. And therefore, we also showed that the probability of the sojourn time exceeds this threshold here exponentially fast as the number of rounds n increases. Okay, so or intuitively speaking, the probability that the earned distribution is often close to a maximal lottery converges exponentially fast. And for this year, we have these delta and tau as before, but now we also have a lower bound on the number of rounds and some constant c, such that the sojourn time for now some finite number of rounds n is at least the threshold 1 minus tau, with a probability that decreases exponentially as the number of rounds increases. Okay, so those were 3 related formal statements about the earn process. And in the rest of the talk, I will first, of course, introduce maximal lotteries, which I haven't done so far, and then show you a couple of examples, which hopefully give you more intuition on how this earn process actually works. So if there are no urgent questions at this time, I can quickly check. Then I'll continue with the definition of maximal lotteries. Okay, so some of you may have seen this slide before because we've been working on maximal lotteries quite extensively in the past couple of years. So maximal lotteries is a randomized voting rule that was proposed by Germain Crévarat and Peter Fishburne independently of each other. And as some of you may know, Fishburne unfortunately passed away about 4 weeks ago. So in order to define maximal lotteries, we take an arbitrary preference profile of the voters. So we have n voters with strict preferences. And then we define the so-called majority margin matrix. And this is a square matrix that for any 2 alternatives, x and y, at the position x, y contains the entry, as an entry, the number of voters who prefer x to y minus the number of voters who prefer y to x. Okay, so this majority margin matrix is the basis for many voting rules, and Fishburne also called these types of functions C2 functions. And once we have this matrix, then specifying maximal lotteries is quite straightforward, because we can just say that the lottery P is maximal if PTM is at least 0. So here, P is just a lottery, so it's a vector of probabilities, 1 for each alternative. And here PT means the transpose of P. Okay, so we have a row vector P, and then this becomes a column vector. And then this says that the product of this vector and this matrix here should be a row vector that only contains entries that are at least 0. Okay, so that's the linear algebra definition of maximal lotteries. But if you're familiar with game theory, you will have realized that this is exactly a maximin strategy of the symmetric zero-sum game given by the majority margin matrix. Okay, so you can just interpret this matrix here as a symmetric zero-sum game, and then a lottery is maximal if and only if it is a mixed equilibrium strategy of this zero-sum game, a mixed symmetric equilibrium strategy. So this is a very nice connection, I think, between game theory and social choice. And the existence of such a lottery is guaranteed by the minimax theorem. And the reason why Fishburne called them maximal lotteries is because you can say that for any... Is there a question?
Can you explain where is the maximin here? I see it is at least 0, but where is the maximin?
Okay, so the maximin is hidden in the fact that we are talking about a symmetric zero-sum game. And that just guarantees a value of 0. So the value of any symmetric zero-sum game is 0. And therefore, by playing this mixed strategy in this game, the role player can guarantee a payoff of at least 0.
Okay, I see.
That's a good question, yeah, thanks. And yeah, so a lottery P is maximal if and only if for any other lottery Q, the expected majority margin, PTMQ, is greater or equal than 0. So in other words, this means that the expected number of voters who are happier with P's outcome than Q's outcome is at least as large as the expected number of voters who are happier with Q's outcome than P's outcome. And according to this intuition here, you can think of maximal lotteries as randomized Condorcet winners, because excuse me, they beat any other lottery, or at least weakly beat any other lottery in pairwise comparisons. But the nice thing is that we all know that Condorcet winners are not guaranteed to exist, but maximal lotteries are guaranteed to exist. Okay, I have an example here which hopefully explains it a little bit better. So here we have a preference profile using 14 voters. And now in order to identify a maximal lottery of this preference profile, we need this majority margin matrix. This we can just get by just for any pair of alternatives, checking how many voters prefer one alternative to the other, minus the number of voters who prefer the second alternative to the first one. That gives the following matrix here. And now in order to identify a maximal lottery, we need to find a row vector such that the transposed column vector here multiplied with this matrix gives a row vector which has non-negative entries. Okay, and in this example, this is quite straightforward because you can see here that there's actually one row in this matrix which only contains non-negative entries. Okay, and that means that this alternative here, alternative C, beats every other alternative in a majority comparison because there are more voters who prefer C than A, for instance, than the other way around, and there are more voters who prefer C to B than the other way around. So C is actually a Condorcet winner. And that means that the vector that we are looking for is a degenerate vector, which puts all probability on alternative C here. And this is, by the way, the case in general. So whenever we have a Condorcet winner, the maximal lottery will put all probability on the Condorcet winner. In game theoretic terms, we also have a pure Nash equilibrium here. So CC is a pure Nash equilibrium. Okay, so in the case of a Condorcet winner, it's easy enough to find maximal lotteries. So let's now change the preference profile a little bit. So I think we are now, for these 4 voters here, we are swapping the preferences between C and D. And then C will not be a Condorcet winner anymore because the 4 here will vanish, will become a -4. And now there's no Condorcet winner in this profile anymore. Nevertheless, we do have a maximal lottery because they are guaranteed to exist. And just as in the previous example, we even have a unique maximal lottery. And that's the following one. So we put 2/7 on D, 4/7 on C, 1/7 on D. Okay, so that happens to be the unique maximal lottery for this preference profile. And if you do the math here, you will see that this resulting row vector here only contains non-negative entries, which is witness to the fact that this is a maximal lottery. So in principle, maximal lotteries can be computed efficiently using linear programming because we are just computing an optimal strategy for a zero-sum game. Okay, so that's maximal lotteries. So the reason why we studied maximal lotteries in so much detail is because they satisfy lots of appealing properties. So I did mention Condorcet consistency already. So whenever there's a Condorcet winner, it will receive probability 1 in the unique maximal lottery. Then there are also beneficial features of maximal lotteries. For instance, groups of voters cannot benefit from abstaining. So that means maximal lotteries do not suffer from the no-show paradox, despite being a Condorcet consistent. This is because we allow for randomization. Maximal lotteries are also invariant under the removal of losing alternatives. By this, I mean that if you have an alternative that gets probability 0, then we can just remove it, and any lottery that was a maximal lottery will still be a maximal lottery. And they also happen to satisfy independence of clones, which is a condition that was introduced by Nicolas Tiedemann in the context of deterministic social choice, and this can be extended to the probabilistic setting. And maximal lotteries actually satisfies a stronger version of that, which is called composition consistency. So, well, I didn't list undesirable properties here, but maximal lotteries, for instance, are not strategy proof. But this is pretty straightforward because, of course, they are efficient, so they satisfy Pareto efficiency. And we know from the random dictatorship theorem that any efficient randomized voting rule that is strategy proof has to be random dictatorship. So strategy proofness we cannot get. But I will come back to strategy proofness at the end of the presentation because we get it in some weak sense for this earned process. So in the past couple of years, we gave complete characterization of maximal lotteries. So the main theme for these kinds of results was that we took an impossibility theorem from social choice theory. Then we extended the setting to the probabilistic model, which also allows for randomization, and adapted the axioms appropriately. And then we got a complete characterization of maximal lotteries rather than an impossibility theorem. So we did so with using errors theory. Yes, another question?
You mentioned if there is Condorcet winner, it is the unique maximal lottery, but if not, then there is maybe not unique.
Yes. Okay. Yeah, good point. So if there's no convergence winner, you can have in principle several maximal lotteries, but they are almost always unique. So you can have a simple example. So if you have majority ties between all the alternatives, then this majority margin matrix will only consist of zeros. Okay, and then any lottery will be a maximal lottery. So that's even possible. So it's not only that it's not unique, but every lottery will be maximal. But these are just degenerate cases. So it can be shown that the space of preference profiles in which there are multiple maximal lotteries has measure 0. But they are not always unique, that's right. So an important subcase where they are unique is, for instance, if voters have strict preferences and there's an odd number of voters, then they're always unique. So this was shown by Lallier et al. Okay, right, so here we took these classic impossibilities and in some sense turned them into axiomatic characterization of maximal lotteries. So one thing that is now important to realize is that maximal lotteries, according to these characterizations, are the only voting rules that satisfy a certain set of axioms. But this earn process that I'm talking about doesn't actually compute maximal lotteries, but only something that is close to a maximal lottery. Right? And therefore, whatever this earn process returns cannot satisfy the axioms, because these characterizations here show that the unique rule that satisfies the axioms is maximal lotteries. That sounds like bad news, but some positive results can be retained, because the axioms here, so I'm very generally speaking now, that I was mentioning here, are approximately satisfied by approximate maximal lotteries. So I think the easiest special case that you can think of is, for instance, Condorcet consistency. So if you have a process that approximates maximal lotteries in the sense that it returns something that is close to a maximal lottery, then the Condorcet winner will not necessarily get probability 1, but a very large probability. Okay, and similarly for the other axioms here, we can do the same thing. So for instance, take population consistency, also known as reinforcement. So originally it says that if we have some lottery P that is returned for 2 different electorates, then P should also be returned for the union of these electorates. And then we can define an epsilon version of this axiom, which says that the lottery returned in the joint electorate should be within distance epsilon of P. And now it can be shown that for every profile and every epsilon, there is some delta, such that every delta approximation of maximal lotteries satisfy the epsilon axiom at profile R. So we are doing this in detail in the paper, and the paper is on my homepage, by the way, so if you want to read more about the details. Okay, but now I would like to use the remaining time to show you some examples of this earn process for some simple preference profiles. So the first preference profile we look at is this one here. So we have 3 voters and 3 alternatives. A is a Condorcet winner. So 2/3 of the voters prefer A over both B and C. And that means there's a unique maximal lottery which puts all probability on the Condorcet winner A. And now if you run the earn process for this preference profile, you could get something like this here. So we have done this for now 50 balls. And this diagram here, so this simplex here, shows you earn distributions. Okay, so every intersection of the grid lines here corresponds to an actual earn distribution. So if the earn only consists of balls labeled A, we are up here. If it only consists of balls labeled B, then we are here. And if it only consists of balls labeled C, then we would be here. And now we start this earn process in the example run here with an almost uniform distribution in the earn. So that's somewhere here. So it's only almost uniform because 50 is not divisible by 3. And then we run this process here. And what happens actually is that this corresponds to a random walk within the simplex here. So we draw 2 of the vertices at random, and then we let one voter decide which of these vertices he actually prefers, and then we walk in the direction of the winner. Okay, so it's more likely that we go upwards than downwards because, well, A is the Condorcet winner. 2/3 of the voters prefer A to both B and C, so it's more likely that we are going upwards. And this path is tilted to the left here because 2/3 of the voters prefer B over C. Okay, and that's why we have this tilt here. The green line, by the way, is the actual earn distribution. And the red line here is the time average of the earn distribution. So the green line here gets close to the unique maximal lottery relatively quickly, and then it just walks around the maximal lottery. Sometimes it leaves this this neighborhood for some periods of time, and then it gets back here. So the green line doesn't the process corresponding to the green line doesn't converge, but the time average shown as the red line here does converge. So one thing that is important to realize here is that this entire process only depends on the majority margins. Okay, so which in this simple profile here is that 2/3 of the voters prefer A to B and B to C and A to C. And that means that if we have many more voters, so let's say we have 3 million voters rather than only 3, so we have 1 million on top of each of these columns here, then the process could turn out exactly as described in the picture here. So it's completely independent of the number of voters. And that I think is quite remarkable, because for these 3 million voters who had these preferences here, after a relatively small number of rounds, so I think it's less than 200 rounds until we have at first 90% of the balls labeled with the convergence winner. So after less than 200 rounds, we are already very close to the convergence winner, but most of the voters have never been asked for their preferences. Okay, it's also a nice approach to just sample votes and not ask everybody about preference relations, need alone complete preference relations. Okay, so let's look at another example, which is a bit more interesting preference profile than one having a Condorcet winner. So this here is the classic Condorcet cycle: 3 alternatives, 3 voters. There's a majority who prefers A to B, a majority who prefers B to C, and a majority who prefers C to A. For this preference profile, there also is a unique maximal lottery, which is the uniform lottery over A, B, and C. And here for this sample run, we had 5,000 balls. And just for the fun of it, for the sake of illustration, we started with a degenerate distribution. So we started down here, which means that all 5,000 balls are of type B. Okay, and then we start this random walk again. And then this green line here describes how the urn distribution actually develops. So we are cycling around the unique maximal lottery, and then it becomes close to a maximal lottery, and then it just stays close to a maximal lottery for most of the time, as the theorem says. And the time average of the urn distributions actually does converge to the maximal lottery. Okay, so if you're concerned about the number of rounds here, so for this extreme example, we needed quite a lot of number of rounds. This process is quite flexible in the sense that we, for instance, need not draw winners in every round. So we could just do these pairwise replacements in every round, but maybe only draw winners every 1,000 rounds, for instance, if the application calls for something like this. So it doesn't need to be synchronized in this sense. Okay, so one more preference profile. Here we have 4 alternatives. So alternative D gets probability 0. And there's again a unique maximal lottery using the probabilities. I can also show it here: 1/2, 1/3, 1/6. And here these solid lines are the actual distribution in the urn. The dashed line is the time average. And this dotted line here, this dotted gray line that you can hopefully see, that one measures the difference, it shows the relative entropy, which is also known as the Kullback-Leibler divergence of the unique maximal lottery with respect to the distribution in the urn. So this is used to measure the difference of probability distributions. And here you can see that it actually decreases exponentially, as the theorem suggests.
When you show the distribution, is it the distribution of winners in the sequence of winners, or the distribution of balls in the urn?
Okay, so that's the actual distribution in the urn. But if the distribution in the urn has the properties that I claimed, it also holds for the distribution of winners. Another good question, yeah. That's not completely obvious, but that's the case.
Okay.
All right. There's some quite interesting related work. Perhaps some of you are reminded of the replicator equation in evolutionary game theory and population dynamics. And interestingly, processes that are very similar to the one that we study in this paper are also studied in the natural sciences. So in fact, about 5 years ago, both Florian and I were contacted independently by physicists and biologists who were interested in our work on symmetric zero-sum games and tournament solutions, because they also studied processes that had these pairwise interactions. And then these processes, or the time average of these processes, converge towards equilibrium strategies of symmetric zero-sum games. So what all of these applications here have in common is that there are pairwise interactions between entities, like could be particles, animals, plants, molecules, and these interactions define a process whose time average converges towards an equilibrium strategy of a symmetric zero-sum game. So here I list the key differences between our model and result and these other ones in the literature, and we think that there are some advantages of our approach, and therefore our results could also be of interest to people in the natural sciences. So first, our model is discrete and not continuous, which is usually harder to get analytical results for. We have stochastic rather than deterministic interactions between pairs and not triples. So some of these results use triples of entities that interact with each other. We have mutations, which is necessary for our results. If you don't have mutations, then all these results break down. And as in the consequence that we have is not only the convergence of the temporal average, but a bound on the sojourn time, which is a much stronger type of result. Okay, so I'm seeing that I'm running out of time, so I just have one slide left. Maybe let me just quickly reveal all these things here. So just recap some advantages of the EARN process. So I briefly mentioned strategy proofness. So it's maximal lotteries is not a strategy proof voting rule, but this EARN process can be thought of to be strategy proof, because if you have a voter that only cares about the current round, then the voter is only faced with the decision between two alternatives, and then within this round it's strategy proof. But of course, if voters are smarter and look ahead, then they can skew the distribution in their favor by selecting alternatives strategically. So preferences are only elicited on an as-demand basis, which is also very good for privacy, because as I explained in one of these examples, we could have millions of voters, and most of these will never be asked for their preferences, which is kind of the best privacy protection you could think of, because you're only sampling some small fractions of the votes. And lastly, so the flexibility I did mention in the beginning. So for this process, it's not required that the set of voters is fixed or that the preferences remain fixed. So voters, we actually don't really care about voters, because all we need is the majority margin matrix. So voters may arrive, leave, and change their preferences. The process will always go in the right direction, which is a maximal lottery of the current preference profile. So we can even add new alternatives or remove old ones once the process is running. Okay, so that one I will skip in the interest of time. So there's a nice alternative interpretation of our results. And the last thing here I have to mention as a computer scientist, because I'm quite fascinated by the fact that this very simple EARN process approximately solves a linear program, because that's what's needed to compute a maximal lottery. So the simple process, which apparently appears in nature, is able to solve a p-complete problem, not NP-complete, by p-complete, and p-complete problems are known to be the hardest problems within p. And in other words, this means that any efficiently computable function can be approximated by this rather simple EARN process, which I think is quite fascinating. All right, so thanks for your attention. I'm happy to answer any other questions you might have.
Thank you, Felix. Great talk. There are some questions on the chat. Arel, do you want to read your question out loud, or prefer me to do that?
Yes, so I was thinking about the practical application of this process. So there are two issues. One is that usually voting is behind the curtain, because I don't want, even if I don't want the people in the voting booth to see what I am voting. So can this be done in this EARN model? And the second practical question is, how do you know when to stop the process and implement the actual outcome?
Okay, well, okay, so let's start with the first question. So yeah, that's a very good question about privacy. So it's, for instance, possible to let a voter privately draw both balls, so that only the voter can see these balls. And then this voter just throws one of them away without letting the other voters know which one it was, and then only declare the type of winning ball. Okay, so that means that the preferences of the voters are protected in the sense that he's not declaring his pairwise comparison. And because the only thing that we need in the end is that two balls are put back into the EARN, but those are both labeled with the winner. So we don't need to know what was the losing alternative. Alternatively, there's another thing that we could do. So we could publicly draw 2 balls, make 1 copy of each ball, and then let the agent privately put back 2 balls of his choice. Okay, so we draw 2 balls, then we make 2 copies of each. So we have a total of 4 balls. And then the voter can put any pair of balls back into the urn privately. And then preferences are protected as well. So that would be my answer to the first question. And the second question was about when do we stop or when do we implement the outcome? So the idea is actually that every round we are implementing the outcome, or every 100 rounds, every 1,000. So it doesn't have to be every round, but we are constantly evaluating winners and implement those as the current winners. So the idea is that this process goes on forever and we never stop.
So, for example, you can think of the urn as the parliament, and the people all the time come and choose 2 members of the parliament, and then replace one with another, and then the parliament constantly changes.
You can think of it that way, yes.
Okay. Cool.
There is one more question from Alex.
Yes, thanks. So I was wondering if you can implement a similar process, but collect the data simultaneously. So as you said, you can sample the data first and then pick the, by data I mean some pairwise comparisons of just random objects by random voters, and then implement your process, and then with probably your convergence results will hold, and that it makes it also interesting. If you can have a simultaneous process
that's another very good question, because so this process is inherently sequential. So in every round we are just drawing 2 balls. So one thing that you can do that I already mentioned is that you need not draw a winner in every round. So you can only do this every couple of rounds, but still we are always drawing only 2 balls for every pairwise comparison. I think Florian and I have thought about drawing like pairs of balls simultaneously, so that several voters at the same time can draw balls. So, but now of course we have to take care, because so more than 2 balls are removed from the urn at the same time. So I think if the number of pairs of balls that you draw is not too large, then the convergence result would still hold. But you have to be careful when you are drawing balls simultaneously.
Thanks, Felix. I see there is a question from Edith on the chat, but it is answered by Florian, right?
So
Edith,
so maybe that's something that I can
ask it. Actually, I have one short question about the interpretation of this dynamic process. Should we think of it as a process specially tailored to converge to the maximal distribution, to the maximal lottery, or we should think of maximal lotteries as a possible point of attraction for many different dynamic processes like that?
Okay, that's another excellent question. So it's of course, the way it happened, the way we wrote this paper is what you described first. So we had maximal lotteries, and then we were looking for a simple dynamic process which converges in some well-defined way to maximal lotteries. But the way we are phrasing the paper now is just that we say we have the simple process. So we start with the process and then prove that it surprisingly converges to maximal lotteries. So I think both of these views are valid, because the process that we came up in the end is simple enough. So we had lots of iterations where we had slightly more complicated rules, but the one that we ended up using here, I think, is simple enough to explain maximal lotteries or the maximin strategies of the symmetric zero-sum game as an interesting, attractive solution. And the fact that there are people in other fields that make similar observations in biology and physics, I think, again, shows that this is a very interesting type of solution.
Thank you, Felix. And I want to thank all the speakers, Florian and Marcus, also for the awesome talks. And now we have a break for 1 hour and 5 minutes. So we continue at 3 p.m. Moscow time. See you soon. Goodbye. Thank you.